everyone, and welcome to the Australia-Israel Scholars Seminar Series. And today I'd like to start by acknowledging the Turrbal and Yagara people as the traditional owners of and their custodianships of the land on which we meet today. I'm in Brisbane at the University of Queensland. And I pay my respects to their ancestors and their descendants, and I extend that acknowledgement to all the lands from which we're joining across Australia and internationally today. So I'm really excited today to welcome Dr. Yafit Cohen, who's a research scientist at the Volcani Institute, which is the agricultural research organization in Israel. And she'll be presenting a talk on data-orientated studies in precision agriculture and in pest dynamics. So Dr. Yafit Cohen specializes in precision agriculture, including fusion of thermal and hyperspectral imagery for monitoring and mapping water status in various crops and orchards, spatial analysis of thermal and hyperspectral imagery for management zones delineation, and the effects of precision agriculture, precision irrigation on yield parameters and water use efficiency. So I would like to welcome Yafit Cohen to begin her talk. Thank you.
Okay, just a moment, I will share this. Okay. So do you see my presentation well? Is it okay?
Yes,
okay.
Perfect. Thank you.
So good morning in Israel. Firstly, I would like to really extend my gratitude to the organizers for this wonderful and blessed initiative. So thank you, Joe. Thank you, Yoni. And also for giving me the opportunity to be part of it. And today I will try to give you a glimpse into the world of data-driven research in agriculture, what I'm doing, and it is already a really a very small part of data-driven research in agriculture. And we will explore various scales of analysis, ranging from the within individual plots to regional levels. And as Joe said, I'm from the Agriculture Research Organization, which is also called the Volcani Institute. It was established in 1921, and it is the research arm of the Israeli Ministry of Agriculture, covering over 70% of the agriculture research in Israel. And we have 6 institutes and 2 centers. One is located in the north and one in the south, and I'm in the central campus of the ARO, of the Volcani Center. And I didn't come originally from agriculture research and not from engineering research. I'm a geographer from Bar-Ilan University with a primary focus, and I'm working in the ARO. My primary focus is on precision agriculture, which I will talk a little bit about that today, and also on spatial temporal analysis of pest dispersion. And one of my objectives in my work is to transform the knowledge that we gain into decision support tools for farmers. Sometimes we succeed, sometimes not. So agriculture is an ever-evolving concept. And over the human existence, it was transformed from animal-powered via machine-powered into data-powered agriculture. And nowadays, we can say that data became the best friend of farmers. I will start with a research that I really like for many reasons. One of the reasons that this study is a unique approach that takes 2 different approaches in agriculture, the conservation one and the precision one. And we show how both of them, which in the first look, it looks very different approaches. I will try to show you that they can benefit from each other. So Cover crops are a major practice in conservation agriculture as it builds soil health and prevents soil erosion. It can help with nutrient trapping and can reduce weeds. These are only some of their benefits and advantages. On the other hand, there is a precision pre-plant fertilization. It can save fertilizers and reduce fertilizers leaching. Dozens of studies address top dressing variable rate fertilization. I mean, after the plants are already out there in the field, but only few research studies address the basal variable rate fertilization, which means we give some of the fertilizers before or even before planting. We give it to the soil and then the plants benefit from this. And for if we want to put precision agriculture is the idea of treating the field variability. So we don't want to put the same amount for the whole field because there is a variability and there are parts of the field that have enough fertilizers or fertilization level and others are not. So we want to make it very accurate in space. So if we want to do that, we have to have the ability to map this variability. And for soil sensing, it requires a very complex systems. So this is why we think that the precision basal fertilization was not so common as the top dressing variable rate fertilization. And this is where we think that crop cover practice can benefit precision agriculture. Because instead, what we're saying is that instead of sensing the soil, which is very complex, we can sense the plants, which are very much easier to sense. So we have a PhD student, Simon Futterman. He's working on that, and our approach is to sense the cover crops, like to reflect what is there in the soil. And we are doing that by remote sensing. It can be either UAV and maybe later with satellite images. And after we are mapping the variability, we can have a prescription map where to put more fertilizers and where to put less fertilizers. So this is the approach, and we started this study in the model farm for sustainable agriculture located in the Northern Research Center of the ARO. It is called Neve Yaar, and it has 5 platforms. I will not talk about it. You can go dive into the site and you will see how the platforms are connecting with each other. And in the field crops platform, we practice both cover crops and precision agriculture. The head scientist is the Dr. Yael Laor of the model farm. And I will not go into the details of the experiment, but we had an experiment with different phenotypes of the cover crops, and we proved that the different phenotypes of the oat as a cover crop reflected what is it in the soil in terms of nitrogen, in terms of phosphorus, and in terms of biomass, which was a very good start to promote the precision agriculture practice. And the field was imaged with UAV. And because we wanted to have something that is not so complicated and not so expensive, we used RGB images. And with a 2-step classification process, of the images, we managed to differentiate between 3 phenotypes of the oat with high accuracy, and the classification is not specific, and we are working on methodology that may be more specific, but this is a really good start. And even with this association, we can produce high resolution maps. You can see here, instead of having a field with one level of fertilization, we can have 3 levels of nutrient levels, and we can use these maps, for example, for smart soil sampling schemes, where to sample, and also to delineate management zones for a pre-plant fertilization application. And of course, it requires further studies, and Simon is working on other approaches to combine with the conservation agriculture practices and precision agriculture practices to save fertilization use, and also to benefit the farmers. So this was a unique approach that I started with, but there are other directions which are more conservative precision agriculture. And the second direction that I chose to present is thermal imaging for core water stress status mapping and to support precision irrigation in cotton. In the first study, we used a very simple UAV images, RGB images, but for some of the practices in agriculture, we have to use some more sophisticated and more expensive cameras, for example, the thermal camera. And why did we use thermal cameras? Because if we want to support irrigation decisions, we need to map the water status, and we have to be very accurate. So the farmers, what they are doing, they are sampling a few plants, and they use a gas chambers that they put the plants into them, and they press some pressure on them to see how much pressure should I put in order to take out a 1 drop of water from the plant. And this is how they know if the plant is suffering from water stress or not. And this directs their decision of irrigation. Now, we cannot use this approach in order to map the variability, because we need to have lots of measurements. So what we are doing, we are trying to choose or select a remote sensing approach that takes images of the whole field to map the variability. And if we take RGB images, it is not enough to see if the plants are suffering from mild water stress. So we need to use the thermal. Now, what is the connection between temperature of the plant and the water status? So when a plant is vital, it makes photosynthesis by the stomata, and when the stomata is opened, it evaporates water and it cools the leaves. So the temperature of the leaves can be a good estimator of the water status of some of the plants, not all of them. So this is what we use in order to map the water status variability. And we started our work from poles. Okay, you can see here the poles 3 or 4 meters above, and we sensed individual leaves, and then we wanted to have larger areas, so we moved into cranes. And then, of course, nowadays we use airplanes, manned or unmanned, most of them, of course, unmanned vehicles. And then we want to speak in the language of the farmers. So we cannot tell them, okay, your plants are 30 Celsius degrees. Doesn't say anything to them. We need to speak with their language. They know what is leaf water potential. They know that because they measure that. So we are trying to take the thermal imaging indices and to transform them into leaf water potential. And this is how we managed to have in cotton a regression model between crop water stress index, which is based on thermal images, into leaf water potential. And all of the dots that you see here are from several experiments in different parts of Israel and in different years and in different varieties of cotton. So this was a good start. And then we had many studies in order to transform this model, this knowledge, into something that we can use for, commercial fields. Again, I will not dive into all of the process, but what you can see here, and you can see here are maps of leaf water potential of a very big field, a very big cotton field. And you can see that here it is in one date along the season. This is 2 weeks later, and this is 2 weeks later, or 3 weeks later. And you can see that the spatial pattern are changing. It means that we cannot use only one time shot. We have to have images every 1 week or every 2 weeks in order to make that the farmer will make variable rate decisions where to irrigate more or less. And after that, we have after we have good maps, accurate maps, reliable maps, we can see whether precision irrigation is better than uniform irrigation. Can we save water? Can we increase the yield? Can we do that? So in this study, we went into a commercial field. We had 2 stripes. One stripe was managed uniformly, how the farmer is doing and practicing, and the other part was irrigated differentially. Each cell was irrigated using the model, using thermal images, of course, and the model that you saw before. And the one that conducted this research was Nitzan Graf, an MA student, which is getting married today, and I'm going to his wedding, so it's very excited. And in the first year, we managed to save water, but we didn't manage to increase yield. In the second year, we managed to increase both the water use efficiency and yield in 20%, which is very impressive. And then we use this approach for a commercial field, and we showed that we couldn't increase yield, but we did decrease the irrigation water with 15%. So this is something that really can help the farmers to make irrigation more efficiently. And we showed this also in a peach orchard, and we are working also on vineyard. And if you ask yourself, how can we apply variable rate drip irrigation? This is because all the drippers have the same status. So another group in our institution, which is led by Victor Alcanatis, they developed multi-status drippers. It means that the dripper doesn't have only one status, only one way to put water, but 2 statuses. And we can change the status by putting a magnetic field on it, and it is closed or opened or partly opened. So we can have a map. Just imagine that we can have a map and a robot that is going through the vineyard, and by the map, it goes into the drippers and change their statuses to fit the map.
think Yafit's just frozen, and hopefully she'll be back shortly.
Also on weeds and the viruses and things like that. And in order to advance our approach in dealing with, in this example, with the Mediterranean fruit fly, we developed an automatic system to monitor the fruit fly. So we have, instead of having traps that are monitored once a week because of labor, we can have data every day, and with our automatic trap, we can have it every hour, every minute, every fly that enters the trap, we can have a time step for it. So we developed an automatic trap for the Mediterranean fruit fly, and we checked it for sensitivity, accuracy, reliability, and we have shown that it is working as well as the conventional traps. And it is very important to show that, because we want to speak with the language of the farmers. We don't want them to get used to another language. Okay, we want it to be assimilated smoothly as possible. And we also show that they are very accurate and reliable in both low in both part of the seasons that the Mediterranean fruit flies are not so active, and in months that it is very active. So we can see that the dots are following very well the gray line. But what is more important, that the fact that we can use this daily monitoring to reduce very drastically the chemicals, insecticides. We had an observation that we used the conventional traps and the automatic traps to make decisions. And while the citrus orchards with conventional traps had, you can see here, had 8 applications, we reduced 3 of them. We used only 5 of them. So it can save like around 40% of the applications, of the insecticide application. And together with that, we cannot separate that from decision support tools. We want to make them more automatic. We don't want to neglect the experience of the service of the decision makers, because they have much more experience and knowledge about the area. But we want to combine decision support tools together with their human final recommendations. So we developed a special decision support systems for the medfly control in citrus in Israel, and we already assimilated that in their environment, in a GIS environment. So not only they can see the citrus plots and the traps, what you saw here is they also see recommendations. Each plot is colored by either blue or orange, red, or light blue, whether it should be sprayed or not, based on different parameters that we assimilated in the decision support system, and it is already working in their environment. They don't need to change anything. They already use this, and they can. And if they go with the decision, okay. If they ask themselves, is it a right is this a right recommendation or not, they can dive into the whole process to see what supported the Metzila. We call it the Metzila. What supported the Metzila recommendation? They can change it by a click. They can change from blue to red, from not spraying to spray, and vice versa. We have shown with an initial initial comparison between people that use the Metzila and didn't use the Metzila, and we have shown that the Metzila can reduce the spraying actions by at least 8%. It sounds not so much, but in amounts of insecticides and in money, this is a lot. Because if you have like, okay, if you want to have more details about it, just ask me. Okay. So if I summarize, and I didn't speak about all the studies, I can say that data-driven approach can benefit sustainability in various management scales in agriculture. We can use cover crops and the variable rate pre-plant fertilization to increase fertilization's use efficiency. This is in the infield scale. We can use remote sensing and variable rate irrigation. It can increase irrigation water use efficiency in the infield scale and also in the field scale. We can use eco-informatics and crop rotation, which I didn't speak about that today, to increase herbicide use efficiency in the field scale, and also to increase insecticides use efficiency in the area-wide scale. So thank you for your attention, and if you have questions, I'm ready to answer.
Thank you so much, Yafit. That was so much exciting work going on in the data-driven agriculture space. Really appreciate it. So everyone online, if you would like to ask a question, you can either type it in the chat or put your hand up and we'll invite you to unmute to ask Yafit a question. I do have a question from Yoni, who had to leave, unfortunately. He said, this is really exciting. And at the University of Queensland, we also have similar agricultural machine learning projects happening. In your experience, how long on average, if at all, does it take to go from idea or experiment to using the research results in industry or on the farms?
This is a really good question. I have to say that I'm struggling with that. So when we started the special decision support system, I have to say that we started it in 2004, and only 20 years after it is assimilated by the farmers. And I think part of it was that the information technologies were not out there at 2004. So we had the idea, we already have the algorithm and all of the things, but in order to assimilate that, we needed to have information technologies that can go into, for example, for all the meteorological stations, and to take the everyday data from there and to connect that with the various stations, various trap stations, especially, and to have the ability to grasp all of this in a minute, okay? Because if you give something to the decision makers and the map will be there after 15 minutes, even 5 minutes, they will not use it. You have to have something that they can use in a minute, in seconds. So nowadays we have that. And also I want to say another thing. When we started to work with them, they didn't have a system on the cloud. Only a few years back, they started to use that. So even if you have this knowledge and how to use all the data, if you don't have the information technologies to assimilate that, it will not work. So this is about the special decision support system. When I'm talking about the monitoring traps, the automatic monitoring traps, we started this 10 years ago. And again, we started with an idea, and then we had to put some time to put it in the field and to see how it works and to change it and to modify that. And then we have to find a company that will take that into a commercial product and to transform the original package that we used into a commercial. This is a very different story, and and this is not so easy. And now we have like 100 traps that are distributed in the fields that are working not so bad. Okay, let's say that it's not so
Is that
bad.
commercialized then, or is that still in the research phase?
No, it is commercialized. It is commercialized,
Oh, wow.
but it's but I know that we will have to escort the company because it's not so easy. And when you want to take it to another place or to another insect, you have to have more research.
Oh,
And
fantastic.
yeah,
I'll just
so
ask Gore to unmute. Gore, would you like to ask your question?
Yes. So I actually have two. I'm sorry, I may have missed it in the beginning because I was late. But how much does something like these technologies cost the farmer? And how does it scale? Because in Australia, our farms are humongous. Like there's cotton farms that it takes you 20 minutes to drive along one edge, or even more.
yeah, so Gur, this is really again a good question. So for the automatic trapping, what we try to do with the company to tell them that there are many companies that developed automatic traps, but they are not as frequently used as we would like to because they are very very expensive. So what we try to do is to make a trap that will not be so expensive. I'm not sure we convince them, but hopefully they will sell that not so expensive as I know about other traps. As for the thermal imaging, what we are trying to do is first to use that as a sampling monitoring tool. Instead of going directly into precision irrigation, we're saying, okay, instead of having a few plants that you measuring, take 2 stripes, because there's so much variation in the field. If you
Frozen moment.
so the thermal imaging will not do anything. But if it is a very heterogeneous field, you can benefit from that. And this is not the thermal imaging is expensive technology.
We're getting some. Sorry, if it's frozen again. Hopefully we'll get her back in a moment. Sorry, everyone.
Management.
Oh.
Oh, sorry. Did
Oh,
I
sorry,
speak to myself?
you froze a bit, but you're back now.
Okay. So I'm sorry. I'm connected to the internet infrastructure in the institute. I don't know what happened.
Very
Twice
strange.
it was. I don't know
Yeah,
why.
I'm sorry.
Sorry. So what I'm saying is that we are trying to use small thermal cameras, which are not accurate, but which with machine learning algorithms, we're trying to make the not accurate signals into accurate signals, taking into account the effects of the environment, of the air temperature, of the relative humidity, the radiation, all of these things, in order to correct the signals that we have from low cost cameras to be accurate and reliable as very expensive thermal cameras. And another thing that we're doing, thermal cameras they have very low spatial resolution. For example, if you take our phones, they have 5 megapixels, sometimes 20 megapixels. This is not the case for thermal. For thermal, 1 mega. So it means that if we need to have high resolution images, we need to fly very low. So the capacity that we can image per hour is very low. So what we're trying to do is to have images from higher altitude and to use super resolution algorithms to make it high resolution images. So we are working on several approaches in order to make this cost effective to the farmers. Sometimes we succeed, sometimes not.
So interesting. We had another question from Ron, and he asks, have you tried automating the processes together to continuously monitor and use the digital dripper so as to have a virtually autonomous farm?
I'm not sure I understand what processes. Can you elaborate, Ron, or because I'm not sure.
I think this was about irrigation and over irrigation with the can't remember how it was monitored. Oh, the color of the leaves, I guess, and whether it can be done like autonomously, syncing the digital dripper.
So we had a study that what we did is to have the cameras on a vehicle that was going, between the rows and taking images of the vines. And there are, not me, but other groups in our institute that are working on autonomous navigation in vineyards. So theoretically, we can do that, but we didn't have a project like you suggested, from continuous monitoring to variable rate drip irrigation. We have bits of studies working on each part separately, but we have some way, even on the variable rate drip irrigation, because nowadays we have to have, like, as you saw, a pole that is very close to the dripper in order to change. And now the Victor and Fanatis are working with not working. They are working on a proposal, okay, with a
So sorry, another delay in the recording. Just wait for your feet to get back.
Maps.
Oh, sorry, your feet. You just
Again?
yeah, I'm so sorry. Oh, she's gone. Oh no. Coming back. I'm so sorry, your feet. Yes, you're back. You're muted now. Can you unmute?
I'm very sorry, really. I don't
okay.
understand. I came to the institute because I said, okay,
Yeah.
this is the most reliable.
Maybe it's at our end. Who knows what's happened? I'm so sorry. So you were saying that they're working on a proposal with, is it industry or?
No, we're working with researchers in order to develop a robot, okay, that autonomously will go between the rows and change the drippers according to a map. So they will work on that. But what I wanted to say is that remote sensing is not a continuous monitoring in time aspect, in the temporal aspect. What we are doing is trying to, again, to connect between the remote sensing, which is once a week or something like that, with continuous sensors that are in situ in the vineyards. So you will have also continuous monitoring, but they're not with high resolution in space. So we have to have the remote sensing for spatial variability mapping with sensors, which gives us a continuous monitoring in time. So this is another thing that we were trying to work on, how to connect between the two sources of data. And also you have to have meteorological conditions that we need to continuously monitor. And yeah, this is why a lot of data that we need
A
to
lot
take
of data goes
Yeah.
into decision making. And then I really like how you always let the farmers have that element of decision, like control over the decisions as well. That's such a important factor for getting behavioral change and uptake.
We're trying to work with the farmers because we think that there are a lot of decision support systems out there which were like a black box. We're trying to work with the farmers from the beginning because this is what we believe will not always, but this is the path to assimilate the technology among them and by them. Otherwise, it will not work. And also, we cannot put in information systems the experience, the knowledge that they have. So what we want is to make the decision, the time of their decision shorter. So they will have more data in, more information, but the final decisions is theirs. So yeah, this is something that we do all the time.
That's really fascinating. I think we'll wrap it up there. And I'd like to thank you so much, Dr. Cohen, for joining us today. And thank you so much to our audience. We've had some really great questions. So please stay tuned for more seminars from the Australia-Israel Scholar Seminars series. We have many more coming from the Volcani Institute, where Yafit works, and other agricultural researchers, as well as others from around Israel and on different domains. So thank you all for
joining. Thank you again,
joining.
Joe and Yoni. Thank you again for this initiative. It's really, really blessed and wonderful.
Thank you so much,
thank you.
Yafit. We really appreciate it. Okay, good evening. Oh, good morning.
Yeah.